and said isometric embeddings. So there will be a little bit of differential geometry involved here, but nothing super abstract. Basically, I'm going to be thinking about two-dimensional surfaces embedded in three-dimensional space. So, you know, the easiest kind of differential geometry that we can work with. So, you know, you've got your surface here. Maybe it's like the upper half of a sphere or some paraboloid or something. And you have some kind of a chart for, you know, some omega open bounded in R2 in your manifold here, call it M or whatever. And we have some chart U, which is, you know, parametrizing this embedded manifold in R3. Maybe I should back up. If you guys don't know what a manifold is, you know, this is a manifold. It's some notion of you know, a subset of or some sort of object on which we can do calculus at its easiest thing. But really think of it for this purpose as some surface embedded in R3. So we can think about this as a chart or a parametrization, this U which maps omega into our manifold. If we want to think about things from like a continuum mechanics kind of perspective, you can think of omega as the reference configuration of some body, like a sheet of paper, and think of U as being the mapping which defines its deformation in R3. So this is maybe one way of thinking about this. And so with manifolds and with mappings between them, we can talk about the derivatives of them. So, you know, you have U. If U is differentiable, we can talk about the derivative du or grad U, which is going to be a mapping from, so at every point x, du is going to be a linear map from R2, taking tangent vectors in R2 into tangent vectors of the manifold. So at every point x, the gradient is going to be a linear mapping from R2 to R3. Normally, I mean, in your multi-dimensional calculus class, whatever, we think of this as a matrix in a 3x2 matrix. So this should hopefully be a little familiar to you guys. So this is the matrix in our case: D1, U1, D2, U1, D1, U2, D2, U2, D1, U3, D2, U3. It's going to take a vector in R2 and spit out a tangent vector to our manifold. So in particular, with these manifolds, we have structure. We can have structure on them, which makes them a Riemannian manifold. This is when you endow your manifold with a metric, some way of measuring distance and angles of tangent vectors. So I'm not going to be too crazy. I'm just going to use the standard inner product that we have in R3 and R2. So if I have two vectors here, so let's say V1, there are two vectors here, V1 and V2, and I'm sitting here at a point X, then at this point U of X, the associated tangent vectors are grad Ux of V1 and grad Ux of V2. And so the inner product between these two vectors can be calculated as, you know, the R3, just dot product really between these two vectors. But, you know, we all know how matrix operations work. we can express this as an inner product between two vectors in R2, looking at this mapping, grad U transpose grad U, as summed by two symmetric positive definite matrix. So this has a lot of, this is, really, it's the pullback of the metric on this manifold back into the plane. And so I don't know, if you've done any work with continuum mechanics, you'll see expressions like this come up a lot of the time. And this is really like what's going on, the pullback of the induced metric on the deformed state back to the reference configuration is given by this sort of symmetrized version of the gradient. So, I mean, if all of that was too crazy, I mean, what we're saying is that it suffices really to see what our distortion U is doing to locally to distances and locally to angles. It suffices not to consider grad U, but really this symmetrized version of it, grad U transpose grad U. Which in general, this is like we're throwing away information when we look at grad U transpose grad U. And in particular, when I talk about isometries, I'm talking about mappings so that this expression is going to be unchanged. So the local geometry under U is going to be invariant. That is to say, mapping so that grad U transpose grad U is just the identity matrix. So this is sort of one way of looking at this. Another way of looking at this is just saying, okay, grad U transpose grad U equals the identity. That means this matrix, this vector, call this, grad U1, dotted with grad U1 is 1. Grad U1 dotted with grad U2 is 0. And grad U2 dotted with grad U2 is 1. And grad U2 dotted with grad U1 equals 0. I mean, this is really just saying that the tangent vector, if I take, E1 and E2, and I transform them into tangent vectors on the manifold, they're going to stay as an orthonormal set in R2 or in R3. So we've got this condition, grad U transpose grad U equals the identity. Sometimes this is written as grad U is in O23, that is orthogonal maps from R2 to R3. And we can look at this as really a system of, like a nonlinear system of ODEs. Like this is really these conditions on the gradient of U1 and U2. This is like a nonlinear system of ODEs. Anyone who's in the SIAM working group knows, these nonlinear PDEs, our normal techniques are not just going to work in general, and we have to exploit special structure that has to do with them, satisfying this sort of geometric kind. In this case, this very geometric kind of condition on this PDE. We're going to have to exploit special structure that we gain when we ask the grad U be in this orthogonal set. So let's look at what solutions this differential equation or this PDE really have to be like. So if I just ask, so I have the U, I'm going to make it into R3, which is C1, and as grad U transpose grad U equals the identity, and I ask you, what do, like this is sort of, okay, if I was trying to start working on this, this might be the kind of thing that I look for. So C1, this is continuous with continuous derivatives. So you might say this should like be hard to satisfy, and it's surprising. It's actually, solutions to this are everywhere. Like there's too many of them. So in particular, there's a result due to John Nash, the famous emeritus of CMU, the guy from the movie Beautiful Mind. This isn't economics. He also did work in BDs. Nash, and also the guy Kuiper in 1955. This result says, so if U0 from omega into R3 is strictly short, i.e. grad U0 transpose grad U is strictly less than the identity of grad U0, then there is U in C1, grad U transpose grad U equals the identity so that U minus U0 in the infinity norm is less than epsilon. So basically, I take any mapping that's strictly short, I can find you a C1 isometry that's always within an epsilon of it, for any epsilon. So this is really surprising. I mean, you can ask what the strictly short condition like means. I mean, if I take any V that's, you know, smooth, sorry, any smooth, any V that's smooth, and I scale this down, you know, 1 over the L infinity norm. I don't know what that is. And I scale it down by, you know, whatever, some appropriate constant. I can make it short. So, for instance, what this is saying is that, you know, if I take, you know, whatever, the upper half of a sphere or something, it's not that distracting to me. If this isn't distracting to you guys, I can just continue, and there'll be fluidness. That's fine. Yeah.
So what do you mean exactly by that means being less than Is that like B times that matrix times another B is smaller?
Yeah. I mean this in the sense that this is symmetric, positive definite. In the sense that, you know, I minus grad U0 transpose grad U0 is positive definite, strictly positive definite. So if I take this and I make it as small as I want, I can still take a sheet of paper, deform it in some C1 way so that it looks like, you know, the surface of a ball with radius, you know, 1/10.
So are the eigenvalues not well behaved, not continuous with respect to the infinity norm?
Are the
this
eigenvalues?
is like the eigenvalues are all less than 1. That's what this is saying. The eigenvalues of A.
Yeah.
Right? And here we have the eigenvalues of this thing are equal to 1. And so here we're saying that I'm thinking like, okay, U is close to the infinity norm, not the gradients.
Yeah.
Okay.
No, I mean, if the gradients were
Yeah,
close,
it's not close.
it couldn't be.
Right, that's what
Yeah.
I'm thinking. Okay.
Yeah. So some of this is really weird. This is like a weird result, and I'll start to talk about. So the theorem, this theorem of Nash and Kuiper, this was like proved in the 50s. It was really non-constructive. So I mean, just like you and me, like people couldn't imagine what these things looked like. And it took this other mathematician, Gromov, he was a geometer, in like the 70s and the 80s, doing some work with this stuff called the homotopy principle or the H principle. It's something geometric. If you want the full proof, it's in a book called Convex Integration Theory. But he came up with an actually constructive way of making these really degenerate kind of isometries. And I'll work through at least the way that you do this in one dimension, and hopefully you'll buy that there's a scheme to extend this to higher dimensions. So let's just take a curve gamma 0 into R3. So just some curve that has the property that gamma 0 prime is strictly less than 1. So this is the kind of thing that we want to do. The trick is going to be essentially, so let's say this is our line, and it's being mapped to something so that distances are always smaller. So some funny thing, some funny curve like this, right? So the distances have shrunk due to gamma. So this is 0, 1, this is some path in R3. So we're going to construct a gamma that's going to oscillate in a way that we recover the original lengths. And to get within an epsilon, we're just going to oscillate faster and faster, so that we're going to pick up the same amount of length with these increased oscillations. And by doing it faster and faster, we make sure we never stray too far from the original curve. So this is sort of the idea behind it. So we've got our gamma 0 that has gamma 0 prime always less than 1. And we're going to define a family of loops, H, which go from 0, 1 across the torus into R3, so that H of t comma s is always equal to 1, and the integral from 0 to 1 of H of ts ds is always equal to gamma 0 of t. So what are we doing here? We've got a family of curves that are periodic in the s variable, in this parameter s. And we want to make sure that that when we average out over s, we're going to redeem gamma 0. So why is this possible? Let's look at the circle. We have gamma 0 prime. So gamma 0 prime is something inside of the circle radius 1. So we can make H, some curve that goes around like this, staying on the boundary of the unit ball. We're going to have average gamma 0 prime. Does this make sense? Okay, I'm also claiming that, so gamma 0 is smooth, I'm claiming H is still smooth here. You could go through this and figure out what they are. I'm going to skip this because it's sort of tedious, but H is going to be smooth in T and S also, as long as gamma 0 is. Do people buy that? Is that satisfying? Okay. So now we can construct our gamma of t for some n fixed. We can just make gamma t, gamma 0 at 0, plus the integral from 0 to t of h of s comma ns ds. So we're just going to oscillate. Yeah.
You lost me on what we're trying to do here. because we're trying to prove this result, right?
Yeah.
So we were looking at maps from surfaces, maps out to
Yeah,
surface.
so now I'm saying, okay, not a map from a surface, but at least a line we can do this.
Oh, so we're looking at a 1D kind of.
Yeah, yeah. So, I mean, okay, the ultimate thing we're going to want to do, which I'm just going to wave my hands for, is you'll say we do this on every line of the surface in some way, and then, I mean, it's not trivial to take this step. There's some work to be done. But you basically do this on every line and induce these corrugations, basically. And this is what's going to get you your isometry. So I'm constructing isometries of the line now. And so if we have gamma of t written this way, where n is, think of this as like the number of oscillations, then I claim then gamma minus gamma 0 and the L infinity norm is less than epsilon. Or sorry, it's less than 1 over n times 2 times the L infinity norm of h times dh dt. So since h is fixed, we can let n be as high as we want. So the proof, well, we've got to prove now infinity estimate, so let's pick any t we want. And we're going to, and write n is the floor of t over n. And look at these intervals. This is for j between 0 and n minus 1. And I n. So we're partitioning basically the interval 0 t.
Should n be the floor of Tn?
Yes. Yep. Yeah. So we're just partitioning up the unit. Yeah, the interval from 0 to t into n pieces of size 1 over n. And then once we have this, gamma t minus gamma 0 is just the sum of these pj's, or pj is the integral over ij of h of tau n tau d tau by definition, and similarly gamma 0 t minus gamma 0 is the sum of some qj's, where qj is the integral over ij of the integral from 0 to 1 of h of t s ds dt. Sorry, I already used t, so plus x. And now we're just going to do a simple change of variables here to, I mean, what we're doing here is exploiting the periodicity of h in that is frequency or period 1 over n. So we'll write So by periodicity, we can write S equals n tau minus j. Identifying things with, like in each of the ij's, we can write S and tau like this. And then doing the change of variables, right? Pj is equal to the integral over the integral now. So tau was going from a length of 1 over n. Now it's going a length of 0 to 1. And we have this factor of 1 over n here. And this becomes h of s plus j over n, comma s plus j. Yeah. Which we can just write as an average over ij. And so now, this is in a nice way that we can compare the PJs and the QJs. So it's a difference of h of s, and that's s plus j, so because j is just an integer, h at s or h of s plus j is the same. And now the difference between these we can bound by we just do the stupidest estimate that we can. So the size of ij is n, the size of 0, 1 is 1, and the difference between h of s plus j and h of x, when x is an ij, is no bigger than dh dt times 1 over n. Just doing, because the distance between them can't be bigger than 1 over n. And then we have a little bit of change, because all this stuff we were doing when we have full intervals, there's the j that didn't get the full way to t, so we have to do pn minus qn. And we'll just do the stupid estimate on this. So this is less than or equal to el infinity over h times 1 over n. Where we're just, doing a really just gross estimate on this. So we sum all of these up because we're estimating gamma of t minus gamma 0 of t ultimately. And then less than or equal to, well, we have n minus 1 copies of these. So n minus 1 over n squared times dh dt infinity plus 1 over n h, and okay, so we can make this 1 over n times whatever I said it was. Are people happy with this? Does anyone have any big problems?
What was the condition in H that allowed us to, I remember the intuition was, right, you wanted to have the same length as the original curve in R2. What was the property of H that let us do that?
This.
This one. And it's 1 for all. It's on the sphere?
Yeah. So this is h of ts is the is what the tangent vector that we're we're choosing.
Right, so
We're
there's
choosing a
one.
tangent vector,
That means it's an isometry. Alright.
h of tau, and
Alright.
yeah. So yeah, this is basically what we do. So we can really do this pretty easily. These are very like simple techniques from analysis for this one. It becomes a lot harder with higher dimensional ones. Basically, this technique, we got a smooth thing at the end of the day. We started with something smooth and we got something smooth. You can only really, in 2D, you can only really get close to an isometry using this technique. So the trick becomes, okay, well, we can get close to an isometry, so we'll get closer and closer and closer to an isometry, and in the limit, we gain an isometry. But as you might be able to guess from this heuristic I drew you, where you have these tiny oscillations getting faster and faster and faster, you're going to lose C2 if you try and do this kind of thing. You're getting too much curvature thrown in. So, but this method really does extend to higher dimensions, and these nice people in France with, it's called the Hagerty project, actually did this for taking the 2D flat torus and mapping this to the three-dimensional embedding of the torus. Are people familiar with what I'm talking about when I say the 2D torus and stuff? Okay, well, so here's some pretty pictures. Can everybody see these? So this is it before they start corrugating the torus. It's just, this nice donut shape. And then they introduce these corrugations. And you see, by stage 2 even, things have become very fine and very, very almost fractal-like in nature. And by the 3rd and 4th stages, it's almost imperceptible the changes that are happening. I'll pass these around, and there's also some nice, they also did renders of them all zoomed in and stuff. So if you guys want to check those out. But yeah, there's like nice stuff. If you look at slices of this object, they look sort of like Coke snowflakes. It's pretty cool. And you can check them out. They're called the Hagerty project. So how much time do I have, Kevin?
7 o'clock. You have 40 minutes.
Okay, cool. So the end of this thing is like, so we can do this business with isometries, but somehow we're breaking the rules. Like, we're able to do too much with these C1 isometries. And the problem is exactly the sort of thing that I was pointing out, that really the important thing about an isometry is less about the, just the fact of it being an isometry, which we can talk about in terms of its first derivatives, and what's really important here is something to do with its second derivatives. And in fact, this is sort of the like punchline or the motivating factor for the study of differential geometry, is the fact that when we're talking about these smooth manifolds, if we know the metric on the manifold, we know about the curvature of that manifold. The curvature, which is something that we can define by looking at how the tangent vector or how the normal vector changes. Something to do with like flatness or curvedness really is an intrinsic concept that's communicated by the local structure of the metric. And this is not what we're seeing at all, really, because when we're just restricting ourselves to C1 manifolds, we're losing the ability to talk about curvature in any meaningful way. So, as we all know, there's this theorem. Are people familiar with this theorem of Gauss, the theorem egregium of Gauss? This says, if you have a mapping that preserves the metric, then it also preserves the curvature. This is why, if you try and map the surface of the globe to a flat plane, there's inevitably going to be distortion in that mapping. because you're trying to map something that has positive Gaussian curvature to something that has zero Gaussian curvature. You can't do it isometrically. And really, C2 is going to be enough. So it's enough to have C2 to get some real structure here. So if now we got that isometries in general are pretty badly behaved, but so if I have U, which takes omega into R3, same picture, but now I ask that U is C2, and that it satisfies this identity, then U is actually what's called a developable surface, or U of omega is a developable surface. What does that mean? These are the surfaces, one definition is these are the surfaces which can be formed by isometrically modifying the plane. But these are surfaces so that at every x, either there is a ball B containing x such that U is affine on B, or there is a line L containing x that hits the boundary of omega such that U is affine on F. So this is a lot more structure that we get. And this really agrees with what we think about when we mess with a sheet of paper. I mean, so if I try and manipulate this piece of paper in a way that I don't crease any edges, but I make it like a 1 centimeter size ball, this is not going to be able to be done. But if I think of developable surfaces, so you can make a cylinder with a developable surface because you're going to have U being affine on each of these lines. Or if I, try and bend it like this over here and try and bend it like this over here, you can see there's going to be this region here where U is going to have to act affine. And this is really, if you ever had to do this in like middle school or something, when you build, you need to build these like towers out of pieces of paper or something. This is what's happening when, paper normally can't resist much, but if you roll it into a cylinder, then it can support weight because it's really going to resist having its Gaussian curvature changed. It doesn't want to stretch, and so since there's already curvature in this direction, it can't sustain curvature in the perpendicular direction. So I found this really interesting when I heard about it, because it's like, this structure is happening less because of anything intrinsic about like the structure of paper or something, other than it's the fact that it doesn't want to stretch or skew. This is the reason that there's structure when I try and push down on a cylinder made of paper. And in fact, C2 is even a little too much to ask. There's stuff going on right now. Mohammed Reza Paksad over at Pitt a couple years ago extended this really to W22 mappings, really enjoyed this same property, like they're going to be still pretty nice. So this stuff really holds even in like these weaker spaces. And so this is what I'm going to spend some more time talking about is the way that these, once you add the right amount of structure in, like C2, how you really are going to get some real rigidity out of these things. And why curvature in the second derivative is really so important even though this seems at first glance to be a first order kind of requirement. So we're going to move now from embeddings of sort of surfaces in R3 and talk for a second about mappings now that take R3 into R3, or omega in R3 into R3. And the motivation here is the fact that, you know, I've been talking about paper so far as sort of an idealized surface, R2 embedded in R3, but I'm really lying when I say that, because we all know paper has a thickness. It's got a small thickness, but it really has a thickness. And so I'm cheating really when I'm talking about it being two-dimensional. And to be honest, we really should be talking about its thickness as well. So talking about a mapping now that takes some subset of R3 into R3. And if we put this same condition on it, that grad U transpose grad U is the identity. Now, so this is saying really, you know, we've got some cube, and we're distorting it to be some funny other shape. You know, U of omega. And I'm asking that at every point, the principal axes are still mapped to an orthonormal set of vectors. And let's add in, this is really just a formality. So just by having this, we know that the determinant of grad U is 1 or -1. Let's say that our map is orientation preserving, just, it really, we're not losing that much generality here. It can't jump in between them. So if it reversed orientation, let's think about it preserving. Let's just, you know, flip it and think about it as orientation preserving. So in this case, the reality is going to be very different. In fact, if I have this requirement, which can be written as grad U is in SO3, then actually what I wind up getting is just that U is affine. Full stop. U, if U satisfies this even in some really weak sense, like U is in W11 with grad U and SO3 for all x and omega. Omega connected, I guess. Then U is actually affine. The proof of this is not that difficult, but it requires some matrix identities that I don't think most people are familiar with. And, you know, it would take 2 pages to prove them. So, I mean, you could find them in Evans, so I'm not going to do them, but I'm going to do sort of the cousin of this. This is another, you know, maybe guiding principle in studying these like nonlinear PDEs is that instead of just studying the nonlinear version, we can get some intuition by studying a linearized form of this. So how do we linearize this idea of grad U being in SO3? Well, let's think about things a little abstractly. SO3 is a subset, it's a compact subset of the 3x3 matrices. And I can't think about 9-dimensional space, so I'm going to draw this just as a ball in R3 because it's a compact set in R3x3. And so we can look at the identity and then say, okay, well, instead of asking that grad U be a member of SO3, we can approximate this by looking at a tangent plane to SO3 in R3x3, in R9, and ask that instead grad u live in this tangent space. So this is what I mean when I say we're linearizing the problem. So now this is going to be a nice linear space that we're asking our matrix to live in. We're paying a little bit. We're going to lose compactness, and we're going to lose some of the nice structure. But hopefully there will be enough structure retained that we'll be able to say something. So does anybody offhand know what the tangent space to SO3 is at the identity? Okay, well, I can demonstrate it really fast. So the tangent space, what we do, we consider some curve gamma of t into SO3, so that gamma of 0 is the identity. So this tells us that gamma of t transpose gamma of t is always equal to the identity. Take a time derivative. Gamma prime transpose of t, gamma of t, plus, so this is just the product rule, equals 0, just the right hand side is constant, and then plug in t equals 0. So we get the identity here and the identity here. So we get that for any curve passing through here with tangent vector gamma prime at 0, gamma prime at 0 transpose plus itself is 0. So these are precisely the skew symmetric matrices that are, or the matrices with symmetric part 0, which are the tangent space of SO3. And okay, so you might say this is only half the proof. Okay, by dimensional analysis is how we prove that that gets all of them. So let's look at this related problem then. Grad u plus grad u transpose equals 0. So this is a nice linear problem that we have to work with. So I told you that we can just work with, say, u and w11. This is still true. So instead of u, let's think about the u epsilon instead. The u, or just a modified version of the u's. So then by linearity, all of these are still skew-symmetric matrices as well. The skew-symmetric matrices are closed under addition, or they're a closed subspace, so you take an average of them, you're still getting a skew-symmetric matrix. So in particular, this means, let me break these exponents up here. Delta I uj equals negative delta j to y. And because these are smooth, we can take further derivatives of them. Equals negative delta I delta j y epsilon.
There's a rocket ship over
Yes.
there.
Is this place going to burn to the ground? Should I?
I think this happens every time.
Okay.
It's still boiling water, so.
Well, I'm going to finish this up pretty fast. Hopefully, I can keep your attention before. Okay, so, yeah. Once again, smooth functions, we can commute derivatives. And we know that, a skew-symmetric matrix, the diagonal is all 0. So delta J of 0 is just 0. And so now we have, so just by these really elementary kind of manipulations, these delta I squared, u, j, epsilon squared are all 0. So if your second derivative is 0, you're affine. So the UJs are affine in every direction. They're affine. So in particular, this means, or, oh, no, sorry. Yeah, each of these are affine. So, okay, for instance, they're all harmonic for one thing. And the second derivative in the I squared direction is always 0. No, this is totally good enough. Yeah. This says that it's affine in every direction, and so it's affine. And this says, right? Is that right? Is this enough?
If it's linear growth, and a harmonic, then it's affine.
Yeah.
So you got the gradient's gotta be bounded.
Well, the gradient isn't necessarily bounded.
Right.
I'm like brain farting up here. It's just messing around with these derivatives in a clever way. So I mean, this at least says these are all harmonic functions, and so their limit is also going to be a harmonic function. So at this point, we can work back with the original u. So we know we have a harmonic function u, so that diuj equals dj ui.
You said you have all combinations of second
Yeah,
derivatives.
yeah.
That should be enough. That means that the
Yeah.
dj
Okay,
ui
yeah, so
is
now, yeah,
constant for
dj
each.
uj is going to be equal to 0 for this. Sorry. I got like lost on this train of thought with volcanoes or something. So, but I think, is it not enough? Is it not enough to just have the second derivative in every direction twice is 0? That should be
And you
enough,
can have
right?
Harmonic functions are going to be polynomials.
This is more than harmonica, though. This is more than harmonic. This is, let's say I just have u, so that d squared iu equals 0 for every I. That's enough to guarantee affine, right? I think that is, yeah.
Harmonic.
I think that's just affine, right? Because then delta iu is equal to some constant. Yeah, delta iu is just equal to some constant.
You have to mix like the outside constants straight, right? Which cannot be
Hmm?
outside constants fixed. Yeah, I think it is. 'Cause
Yeah, you're right. So this isn't enough. I'll come back to this. I'm sure it's really not hard. It's just another, like, you take a derivative in a clever way. And for the same reason,
Is it just?
I'm gonna give up on proving this right now, just because I'm clearly have no brain for it. But
Trust me, it's true.
and so is this. You get affine out of it, which is really a lot stronger than what we got for embedding a two-dimensional thing. So a two-dimensional thing, if we asked for the curvature also to be, you know, under control, or at least well-defined, we could still do a lot of things with our surface. And yet here we're saying that when we ask for this to be a body in 3D, you can't do anything. You can just do rigid motions, and that's all you can do. You can take a rotation, you can take a translation, but you can't, you know, bend whatsoever. You can't do anything non-trivial. So, I mean, the question, like, okay, question number one is, so how come I can bend paper? And like, what's really keeping me from doing this? I mean, the sort of heuristic that I keep in my head for why you can't do anything interesting with a three-dimensional object, I mean, there's all of this stuff, but what's going on is, so, you know, you've got a unit cube here. You've got a unit cube here, and you try to, like, you know, bend it at all. So if I tried to bend like this, let's say, the way that I could bend a sheet of paper, then I'm changing the distances up here. I'm doing what I'm not allowed to do. Like being unable to change any of the distances in a cube, just the distances between, you know, let's say I made a little wireframe and fixed all of these, we know you can't, you're all automatically locked. You can't do anything fun with it. This is somehow, I mean, this is just a heuristic. But this is how I try and think about this stuff. Let's see, what else do I want to mention? Oh, you can get quantitative. I told you that grad U and SO3 and grad U transpose grad U equals 0. I tried to show you. We'll leave this as an exercise. It's not that. If you assume that it's smooth, just try and get that this gets you affine, because I swear it's just messing around with these things. It's not hard.
That question is just for the tangent space, right? That you want the original U to be affine, not the tangent space version.
Yeah. I mean, so this is also true. If you have grad U and SO3, it's affine. And like I said, it uses, I mean, the proof is the same sort of, just you're messing around with these matrix identities, but you have to use like the cofactor matrix of a gradient is divergence free in the rows, which is well known to people who do these kind of things, but is not. I mean, I would have to remind you what a cofactor matrix is for one thing, and then it's a 2-page proof in Evans that's not particularly enlightening why these have divergence free rows. So I figured if I'm gonna like tell you one thing or tell you another thing, I'm just gonna tell you that grad U and SO3 it implies affine. So you can get quantitative estimates on this. So the integral of grad U, you know, if you're in the right integrability space. So there's a constant which says that you can control, if I have control over, say, the distance squared from grad U to the space of rotations is under control. There's actually a particular rotation R that I can control this by. So quantitatively, if I'm not just being in this set tells me that I'm affine. Being close to this set on average means that I'm close to a specific affine transformation on average. This is a result by Friseca, James, Mueller from a couple of years ago, which is basically the starting ground for a lot of work on plate theory. And similarly, there's a quantitative estimate which says that if I can bound the symmetric part of a gradient, then this is going to give me control over the whole gradient, in particular giving me control over the distance of the gradient from a particular affine transformation. You can think of this as like Korn's inequality, basically, is what this is telling you. So this is something that I thought was like mystical, I guess, when I first saw it. It's Korn's inequality says that if I want to control the L2 norm of the gradient, it's enough to control the L2 norm of the symmetric part of the gradient. And this is really, I believe, where it's coming from, the fact that if you can force the gradient to be basically skew symmetric, then it's got to be essentially an affine function. And you can make this quantitative. And I think, I don't want to get into any other stuff. So this is where I'll leave it. And thank you all for your time.
Any questions?
All right, thanks again for your time.